Remember that, unless, look at the canvas first, and then if I tell you to look at the lab book, that's my problem. Then you can do it. So here we go into the canvas. And here we go into the assignment. And here we go into the analysis of baking soda here. And this same thing is also given in the file as PDF copy and as a regular copy. So both copies are there in the file. So we go here, analysis of baking soda. Use the following procedure and instruction about the procedure given below. Oops, that doesn't make sense. Use the following steps and instructions about the procedure given below. Steps, sorry, not procedure. Do not use the procedure and the other information given in the lab manual. Okay. So, number 1, start virtual chemistry lab, select acid-base chemistry. All right, let's go over there. We're going to start virtual chemistry lab. Beyond labs. Oh, beyond lab portal. There we go. Logging in. Okay. Now, one person told me that they don't have the ability to get into the lab. So that person, I have been asking around, but I have not gotten any satisfactory answer yet. I did get some answers about how to do that, but it was not satisfactory enough. So I cannot tell you anything. In the meantime, there are 2 options I can give you. One option is you work with somebody else. And if you have a computer, not a cell phone that you are working with, then life can be easier because you can share this with somebody else, and that's fine. 2 people can do the experiment together. I don't mind that, but no more than 2, please. This lab is, I'm going to leave it to your conscience. When I say 2 people work together, that's okay. No more than 2, and everybody has to have their own report. And 3 people, please don't work together. It's just for you. If you work for 3 people, the chances of you understanding decreases a lot. Okay, that's why. Acid-base chemistry is where we are going, and study, and the last part is analysis of baking soda. This is where we are going. Acid-base chemistry, analysis of baking soda. So here we go. Now, I was saying to this person, so you can work with somebody else if you have a computer, or you can work with me. And if you need to work with me, and I can let you work on my computer, I can find some time that is mutually acceptable for us, and then we can do it together. But you need to let me know that you want to do that. Then we can work on it. So this is where we are at. NaHCO3, unknown number 13. So that's what we need to write it down. Everybody got to have that unknown, otherwise I cannot do much with your stuff. I cannot tell you how good you are. All right. So we need to read that. So let's go. Start virtual lab. Okay. The stirring plate with 1.500 grams of impure solid baking soda. So this here already has impure baking soda, not pure, not 100% pure, impure baking soda. This here, this already has impure baking soda. It also has an indicator that will tell us when the reaction is complete. So sufficient water to add, making the volume 25 milliliter volume here. Methyl orange indicator will also be added to the beaker. That's already done. The impurity in the baking soda does not react with the acid. So we don't have to worry about the impurity, meaning this is not 100% baking soda. An analysis of the baking soda means we want to find out how many percent of this solid is baking soda. Really, not baking soda, is sodium hydrogen carbonate. That's the ingredient in baking soda that is the active ingredient. The rest are passive ingredients, passive. And the passive ingredients are not working, reacting with the acid. Only the active ingredient is reacting with the acid. Click on the burette zoom view. The burette will be filled with 0.3075 molar right there. Molar is here. The burette is already filled. We don't have to do anything. Click the save button in the burette zoom window so that zoom window, save button in the zoom window. Okay. Okay, save button in the zoom window. Save button in the, okay. Save button in zoom window. Okay, the horizontal position, orange handle, everybody knows that about that. So we're gonna open this and let the acid out in the mixture of baking soda and water. Now, there is a blue line. Okay. Open the stopcock. We read that vertical position. We know that. Turn off the stopcock. Okay, fire. Observe the titration curve. Observe the titration curve. You don't need to do anything with the titration curve. You don't need to tell me anything. Just observe. And the blue line will meet the red line, and soon it will start to turn down. Then double click the stopcock to turn it off. So I'm gonna get ready to turn off the stopcock. See, I double click, it turned it off. This is what I'm talking about. Now, if I double click, it opens up. Now, I'm gonna double click because now I see that the blue line is, hey, going down. Oh, good, good. Stopped and it changed color. So that's what I'm gonna write down, 39.91. 40, this is 39.9 and a little bit more, 39.91. Maybe I have a little bit too much in here. First time that can happen. So this is what you are doing 3 times. So let's see. The blue line will meet the red line and soon it will start to turn down. Then double click the stopcock, turn it off. Move the stopcock down 1 position to add volume drop by drop. That's what we did not do because I was trying to explain to you. Okay. Stop this tri-system when the color change occurs. Click the stop button in the burette zoom window, stop button in the zoom window to save. And your notebook over here. So you work it out how to work with the notebook. And if you don't know how to work with the notebook, just write down the numbers. Repeat the above procedure 3 times. You may have different unknown number for each trial. Record your results in the data table shown below. So this was number 13. Do not include the above procedure in your report. I don't want this above procedure in your report. This is what your report is going to have. Data table. Do not include any pH or conductivity data in your report. Your report will have the data table, calculation, and tabulated results as shown below. This is what I want. This is what the report is going to start. You're going to say, report on analysis of baking soda. That's your title. And then data table. And the data table is going to be like this. And it would look like this if I draw it. And I want this professionally done. No haphazard thing like that. I don't want it like that. I don't want it like that. I certainly don't want it like this. Oh no, like this. I saw some people doing it like that. Please, you are in chemistry 1A, you are in college, you can't do that. So I want a proper data table that looks nice. I mean, there's not much to it. You can just use a ruler. Not a big deal if you don't want to print it. At least it should look this okay. This is a little bit too much, but it's not too bad. Unknown number 13. Mass of impure baking soda. It was 7 point something here grams. was given up on top here. How many grams was it? 7 point. Oh, 1.5 grams of impure solid, not 7. Okay. Stay there. $13, unknown number. Mass of the impure baking soda, 1.500 grams, whatever. What is given? I think 4, 5, 6 figure are given. Mass of molarity of the acid. What is the molarity of the acid? Somebody tell me.
0.3015.
0.3015 m. Milliliter of acid used. We use 39.91 milliliter. And you have 3 like that. If you make 4, if you want to do 4, that's fine with me. I want at least 3. Okay, calculation. So one sample calculation. You will have 3 calculations, of course. You're not going to show me all 3 calculations. You're just going to show me one sample calculation. So write a balanced equation. For all 3 trials, calculate the mass of sodium hydrogen carbonate in the impure baking soda. Also calculate the percent sodium hydrogen carbonate in the impure baking soda. So everybody is doing the calculation for this one trial that we did right now. And first you are going to write the solution map. And then you are going to do the dimensional analysis, do the stoichiometry. And I have shown you how to do that. In this case, it is going to be liters to moles, to grams. That is your solution map. Liters of acid, to moles of acid, to moles of sodium hydrogen carbonate, to grams of sodium hydrogen carbonate, SHC. Make life easier for you. Call it SHC for sodium hydrogen carbonate. I have given you the solution map. I want everybody to do this right now and get the answer. And you have 5 minutes or less to finish this. This is not much at all.
Professor. Oh, he's gone.
Has anyone done the molecular equation yet? Or the chemical equation?
I think it's just one across the board, right? Because it's
All right.
Na2. Yeah. No, because there needs two of those. Both no CO1. So I think it's Na2 HCO4 plus HCl equals H2O plus Na2Cl plus CO4.
Okay.
Right?
I think so. I haven't written it out yet. I'm stepping away.
Do you know what the liter to mole ratio is for FHC though? It's not given.
I think, well, we have the molarity of the HCl, right?
Yeah, but not of the.
I think as long as you have that molarity and you do a mole to mole to grams, you should be able to do it.
Well, but we have milliliters.
We have liters.
We have milliliters of SHC, not milliliters of HCl.
And we have the, isn't it the molarity
no.
of HCl?
No. We have milliliter of HCl. These are milliliter of HCl right here.
Yeah.
HCl was in the burette, and solid NaS, solid sodium hydrogen carbon, solid baking soda was dissolved in water, and that is over here, and that is, we are given 1.500 gram of impure baking soda.
Ah, that's where we start.
Now, we are not going to start with that. This is impure. We cannot start with that. I told you liters to moles to gram. That's what I gave you. Is that right? Yes?
That's what I'm solving for.
Liters of base, and liters of acid, 2 moles of acid, 2 moles of sodium hydrogen carbonate, 2 grams of sodium hydrogen carbonate. This is what I gave you.
And Professor, it's a 1-to-1, right?
Yes, it is. Because when you write the equation, that's how it's going to work out to be. So
You said it's okay if I just write SHC?
yeah, so it seems like what the problem here is that people don't understand why this is the case. What are we trying to find? This is not very clear to some of you. And that's what you need to ask me. That's your question. What are we supposed to find? We are trying to find, we are analyzing baking soda. We want to find out how much sodium hydrogen carbonate is in 1.5 grams of baking soda, which is not pure sodium hydrogen carbonate. So we need to find out how many grams of sodium hydrogen carbonates are there in 1.5 grams of impure substance. So 1.5 grams is an impure substance. It cannot be in calculation like that because this impure substance is not reacting. Only part of it is reacting. We want to find out how much of it is reacting. And therefore we do liters to acids, 2 moles of acids, 2 moles of sodium hydrogen carbonate, 2 grams of sodium hydrogen carbonate. That's the part that is reacting in this 1.5 grams. That's we have in this beaker with the reddish liquid now. That's what we have. This is what we need to understand first. So once we understand that, we find out grams of sodium hydrogen carbonate. And that a calculation now everybody should be able to do. So let's finish that calculation. Before that, you would have to write down the equation. And everybody, I thought most of you are not bad with equations. Couple of you need some more help, but most of you know how to write equations. So that's good part. So you would have HCl, AQ, always AQ for the acid, please. Not 9. AQ. HCl, AQ. Plus NaHCO3. And this is a gas formation reaction. This is a double replacement gas formation reaction. So you are going to have carbon dioxide formed and water formed and NaCl formed. This is your balanced equation, already balanced. So it's a one-to-one relationship, as somebody was pointing it out. So now you have everything that you need to do, you need in order to do this stoichiometry. So I want to see a neat stoichiometry done like that. And I want everybody to show it to me. So I'm gonna turn this off. I'm gonna stop sharing my screen, and you're gonna share your screen, and you're gonna show it to me.
Wait, Professor. So
Yeah.
why would it be SHC?
A good question. Why would it be SHC? What is the purpose of this experiment? The purpose of the experiment is to analyze the baking soda. What do we mean by analyzing baking soda? That means we want to know how much of this baking soda is really reacting and how much of it is not reacting. Analysis of baking soda. We have 1.500 grams of impure solid baking soda, which is not totally sodium hydrogen carbonate. So we want to find out, is this 60% sodium hydrogen carbonate? It is 90% sodium hydrogen carbonate. How much it is sodium hydrogen carbonate? So we need to find out how many grams of sodium hydrogen carbonate are in here in 1.5 grams. Does that make sense now?
Yeah, so would it just be like other dimensional analysis problems where you have to find the molar mass of SHC?
We already know the molar mass of SHC given to you. Good, we need the molar mass. You are right about that.
Just curious, what did you get for molar mass? Just so I don't have to do it.
Oh, we have the equation. We know
I
the,
know,
the
but-
sodium hydrogen carbonate, so we can find the molar mass.
If anyone
Everybody go
already
find the molar mass if you don't know it. If you haven't found it, find it. Go ahead.
all right, I'll do it.
The molar mass, everybody should get 84.01 grams per mole. So now, anybody who is done with the stoichiometry with the setup, they want to take over and show the stoichiometry setup to me. So I'm gonna get out of sharing this and you are gonna share it. So here you are. Who is ready?
I can do it.
Okay, good. Show it to us. If you can.
All right, can you see? Sorry, I'm still doing the.
That's
I'll get this molar mass right now. 1 second. I know you just said it, but.
molar mass 84.01 grams per mole.
Is it 84.02?
0102 is okay. Okay, now please cancel out all the units that you don't need.
Well, so 1-to-1, HCl, cross, 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 cross. Yep.
Could you
See.
show that to us?
Yeah.
Actually cancel it.
It should be. They all cancel out, right?
Yeah, but could you show it to us, like, cancel this milliliter of HCl with a milliliter here?
Okay. Yeah. So we start with milliliters. Can you guys see my mouse? Okay. So we have milliliters HCl. I just did this. You don't necessarily have to if you just know.
Right.
But milliliters cancel to give you liters. Then you have the molar mass or the molarity, and so you're canceling out your liters to find your moles of HCl. And then you know it's a 1-to-1 based on the chemical the chemical equation. So you have 1 mole HCl that cancels out with the moles HCl here, and then you have leaves you with 1 mole SHC, and then 1 mole SHC cancels out with the molar mass to give you grams SHC.
And so now somebody else is going to do this calculation and tell us the answer.
I'll do it right now.
Zachary, please tell us the answer.
It's 10.11 grams.
Thank you. Write it down, please. Joshua, you have the control here.
Yeah, my bad. 10 point what?
10.11 grams. We'll take 4-6 week, that's fine. That's good. All right. 1 point, not 10 point. Sorry, 1 point. 1.011 gram, is that what you got? Zachary?
I did get 10.11.
I got
I think
1.011.
it's different is because the milliliters instead of liters for
okay.
molarity.
All right. How did I know it was a wrong answer? Because we have 1.5 grams of impure substance. It has to have less than 1.5 grams in there. That's why I thought that there was a problem with the decimal point. All right, good. Now, step 2. Calculate percent sodium hydrogen carbonate in the impure sample of 1.5 grams. Everybody knows how to calculate the percent. So let's do the percent.
You want me to stop sharing? You want me to just do it on here?
Stop sharing now. Somebody else is going to do this percent part.
How do I do this? Here we go.
Anthony Daise, you're going to do the percent. Take control of the, can you do that? Take control of,
Oh, so I'm working on a piece of paper.
good. Piece of paper. You can show us the piece of paper if you don't mind. Just write it a little bit big.
Oh, sorry. I didn't hear you, Professor.
I want to show, I want you to show us how to do the percent.
Okay, yeah. So
Percent
I'm
sodium
still
hydrogen
working on the
carbonate,
paper.
impure substance.
Oh, so you want me to just explain to people like the process?
Could you show it to us? And then you can explain.
So like I said, I'm working on a paper, so I don't know how I can like show
All
you.
right. Okay, then explain to us.
Yeah. So since we have like 1.5 grams of the baking soda, so we're gonna say 1.500 grams divided by the total mass of the baking soda times 100.
And what is the total mass of the baking soda?
Let me see. Let me try to write that on a piece of paper. So I think we just,
I don't know if that works.
Here.
I don't think that's the right answer.
I'll share my screen.
oh, thank you.
Okay, Anand Daise, tell me first.
Okay,
What is percent?
Sorry?
What is percent?
percent, we just multiply by 100.
Percent, what does it mean in English?
Per 100.
Per 100. Why are you saying multiply by 100? Per 100. What per 100? X per 100. If I say I have the milk is 3.5% fat, what does that mean? 3.5% fat. How would you write that? As a fraction.
3.5%.
As a fraction, how would you write that as a fraction? What would be in the numerator and what would be in the denominator?
3.5 on the numerator and 100 at the denominator.
Thank you. So 100 is the whole and 3.5 is the
Numerator.
part in the numerator. So now go back to that and tell me which one is the whole and which one is the part. 1.500 gram of impure baking soda and 1.011 grams of sodium hydrogen carbonate. Which one is the part and which one is the whole?
I think the part is 1.5.
1.5 is the whole.
Okay, Joshua, you wanna ask? You wanna explain why 1.5 is the whole?
Well, so we're finding the percentage of sodium hydrogen carbonate inside the impure sample. I mean, one, you can see that the larger number is going to be the whole compared to the smaller number, but two, because we're trying to find the percent of what we just calculated, the 1.011 grams SHC inside the impure sample of baking soda. So we know that the whole is going to be baking soda. And then you're going to divide the part by the whole times 100 to give you the percentage.
So if we have 2 sig fig, the answer is going to be 67%. Is that right?
Yeah.
Okay.
Wait, Josh, one more time.
Yeah, what's up?
It's 1.5 minus 1.011 because I got 32%.
I'll share my screen. Can you see it?
Yeah, I can see it. Oh, it's opposite.
Part divided by whole multiplied by 100. You need to decide which one is the part and which one is the whole.
Oh, wrong pipe.
Thank you.
Of course.
All right. Now, the next part is where is my next part? I need to share the screen now. Here is the next part.
Professor, can you run through the first calculation one more time? I keep getting stuff that's over 1.5.
Thank you. Very nice. Good question. So, can you tell me the solution map?
Yeah, it goes liters of acid to moles of acid to moles of the sodium hydrogen carbonate to grams of the sodium hydrogen carbonate.
Excellent. So now it's just a simple question of multiplication and division. And Joshua, you take over again because you already had it written down. So show
Yeah.
us that. So here we are. 39.91 milliliter converted into liters, and then 0.03991. Are you writing it down on your calculator?
Yeah, yeah.
Okay, so that's going to be 0.03991 multiplied by 0.3015.
Oh, I realized my mistake. My
Good,
conversion
wonderful.
factor was
When
1
you,
liter
when
to
you see
100
your own
milliliters.
mistake, you make me happy.
I definitely made that mistake too, where instead of moving the decimal place over 2 or 3 spots, I'll move it over only 2. That's why recently I've just been writing the whole thing out because it just makes it so you have less mistakes.
Okay. All right. Now the next part. So let's go down there. So result is going to be this. This table got discombobulated here, but you will have to figure it out how to there. The table looks much better if I expand it. So unknown number, mass of sodium, hydrogen, carbonate. This is the result. So you say result on top like that. So you show your percent. You say step 2, percent calculation, percent sodium, hydrogen, carbonate calculation. That's your heading. And then underneath you show one calculation only, not all 3. And then the results that you get, you are going to write down in a table, neat table like this. Now, these are the 2 problems that you are going to do for the post lab. And I'm going to help you out by, this is a 3-point thing here, right here. And you're going to do this. And if you need help, we're going to help you and we're going to get it together. And this is part of your review for the exam. So let's go. 238. Let's take a break. And then we go. All right. So that's what we are doing the next part. These 2. And that's review for the exam. All right. 239, 240, 15-minute break or 10-minute break?
15.
Either way.
15.
All right, 10-minute break. We'll be at 2:50. At 2:50, we'll be back. I'm gonna turn off the sharing right now.
The recording has stopped.
Hey, Professor.
Okay. Where am I doing? What am I doing? Oh, that's the-
I do, Professor.
Good. Let's see.
Do you want me to send you like a separate message, like an email or something, maybe?
No, I write it down right here, right now.
Okay.
Okay, one person wants it. I hope you can pick it up when they are going to give you certain time. But I had to tell
When
them.
they do like a campus pickup, they do it morning time, and I'm not. Usually I don't have. I can't even talk. Usually I can't go because I have to work in the morning.
Well, is there somebody else who could go, who could pick it up for you? I asked about that, and they said that's okay as long as you fill out your form and tell them that that's happening.
Well, because that's what happened last time. I had I think Cindy or
Well, that's why I made sure this time that if that happens, it will work. Last time it was not arranged that way, so they had said no.
Okay, sounds good. Thank you.
Mhm.
No, but last time I guess they said they had a number of students but not enough copies, and that's what happened to us. I
Sometime,
got there to pick up for others, and they said that they had run out.
also one person told me last time that they did not let
Yeah, no, they weren't allowing.
us, right? But this time they will because I checked with that. Okay, but
Okay.
you have to fill out the form and send it to them, and then they would let you.
Okay.
So I'm counting now. How many students? Why?
Yeah, that's what I was gonna ask. Would they have enough copies? Because last time they said they ran out.
Well, I'll have to make sure they have enough copy. Okay, so that's why I am asking right now how many students are going to go, so I can tell them how many copies are needed.
Okay, I'm gonna go.
So 2. And you are picking up for somebody else. That's 3. No.
Yeah.
3. Okay, time to come back. I have 2 questions. How many students still need molecular model and the drawing pad? So I can tell them that, and I find out that they have enough, and then I can tell them to send an email, or I can send an email to the class, and then you have to fill out the papers and send them back to you. And then we'll know when you can pick it up. That's number 1. Number 2, I have so far 3 people told me that they would want to do that. They would need that. And one of these 3 people cannot go, but another person would pick it up for them. And the other thing is test 2 is going to be next Tuesday, and 1 hour 45 minutes, Tuesday morning till Tuesday night, in between the times. And 70 points, but it will be saying 75 points because there are going to be 5 points bonus points. So that's why it's going to be that way. So let's go to these problems here. Post-lab problems number 1. Suppose impure sodium carbonate, not sodium hydrogen carbonate, but sodium carbonate. 95%, the impure, it was 95% sodium carbonate. was used instead of pure bicarbonate in above experiment? A. Calculate mass of pure sodium carbonate needed to react with 40.30 milliliter of hydrochloric acid. So let's do that first. You are doing that first. It makes it easy for you to write down the solution map first. So write down your solution map, and then remember there are 4 parts: grams to moles to gram, or grams to moles to liter, liters to moles to liter, liters to moles to grams. I wanna see the 4th part. That's what that is. America.
Hey, Professor, I'm sorry, I just caught on. I need a the molecular model and drawing pad as well.
Good, good. That's good. So I have 4 now.
I do also.
5,
So do I.
6.
So next Tuesday at
I don't know. That's most likely next Tuesday at between 10 and 11. Most likely, but I don't know that for sure.
oh, to meet with you?
No, no, no. The picking up of this thing.
Okay.
And you are not gonna see me then. If somebody wanted to pick up the guidebook from my home and they have not done it, I don't know. Okay, America, can you tell us your solution map for this problem number 1? Are you there yet?
Yes, give me a second.
Okay.
So it would be similar to the other one where we start with milliliters and then go all the way
We
to
just go to
grams,
liters.
right?
We don't care about milliliters. Just
Okay.
2 liters. Okay, liters to liters of substance. Yeah. Sodium carbonate or acid?
So wait. Acid,
Good. The next step.
moles of acid
Good.
to moles of base,
Excellent.
and
Yes,
then grams.
and grams of SC. Got it done. All right. Now, everybody go ahead and do the setup and get the grams. And I want to see it neatly done for your sake. I'm not going to see it. Or maybe I will see it. Maybe you will share it to me. Fran, how are you?
Hey.
Tran, how are you?
Good. How are you?
All right, I'm all right. So when you are ready, could you please share your screen if that's possible?
I can't find the page. I'm still trying to find it.
Oh, the page right here. Don't need to find any page right here. Can you see my screen?
Yeah.
Yeah, that's where it's at. And it's in the, for later, it's in the Canvas on assignment, and it says analysis of baking soda. So that's where the page is.
Yeah, I click on that and it's nothing is showing up.
Oh, huh. Well, just deal with it right here, right now.
Okay. What do you want me to do?
Yeah, I want you to do the setup for this problem, liters to moles 2 grams of SC, and show it to us, the stoichiometry setup.
Show it to you?
Yeah.
I don't know how to do it. Maybe you could show me.
Sharing the screen? Sure, I can show it to you, how to share the screen, okay?
Oh, can you show me how to do it?
Huh?
Can you show me how to do it?
No, I cannot show you how to do it. I can help you with it. So we can do it together, but I'm not gonna tell you exactly what to do. So liters of acid, where are the liters of acids?
I honestly have no idea what you're doing.
Are you reading this?
Yeah, I'm reading it, but I have no idea because I just joined like not too long ago, so I'm kind of confused.
Okay. Well, everybody just joined 10 minutes ago, right? Okay.
So the
let's
liters of
read
acid will be
together.
your M hydrochloric acid, right? That'll be the 0.3015.
That's right, yes. Suppose the impure sodium carbonate was used instead of pure bicarbonate in the above experiment. We use the bicarbonate here. In this experiment here, we use bicarbonate. But instead of bicarbonate, somebody used it instead of that impure sodium carbonate, and 95% sodium carbonate in that substance. And then the reaction was carried out. Calculate mass of pure sodium carbonate needed to react with 40.30 milliliter of this many hydrochloric acid. And then we were good to get this solution map. Liters of acid to moles of acid to moles of sodium carbonate to grams of sodium carbonate. Now the next question is, how many liters of acid are we going to put here?
Is it 0.3015
Is that liter or is that molarity?
molarity?
That's not liter.
Is it going to be 0.0403?
That's correct. We are going to convert this milliliter into liter. You can just do it in your head, or you can write it down. However it works for you. It works fine for me to write it down in my do it in your head and then write it down. So that's going to be 30 liter acid. And what are we going to multiply it with? That's a conversion factor. Tell me the conversion factor. What is going to be on the numerator and what's going to be in the denominator?
1 liter on a denominator.
In the denominator. Very good. In the denominator, because we want to cancel the liter.
Yeah, 1 liter.
And what is in the numerator?
0 point something. What is that? 0.3015?
Very good. And what are the units?
Mole.
Excellent. Hey, you know these things.
Yeah, I just don't like when you call me out.
I'm sorry. Thanks for being honest about it. I appreciate that. All right. Now we're gonna go to somebody else. Let's see. Gonzalez Soto. Let's go to you. What are we going to do next? All right, so tell us the how are you going to do that?
Sorry, Professor, to interrupt. I have a question. Do we need to turn this in?
Do we need to turn this in? Yes, you will need to turn this in, and you're gonna get 3 points for that. So I'm giving you with 3 points right now. But
Okay,
you know, you have time. You're not gonna do it today.
Who's cutting out?
So, Mr. Gonzalez Soto, keep on going. What do you say? Very good. So, who is going to help us write the equation? Next person?
It'll be 1 mole SHC over 1 mole HCl.
Well, let's write it down. Na2CO3, Na2CO3, sodium carbonate, plus
HCl.
HCl. And what are the products?
NaCl plus H2O.
Plus CO2. Very good. This is what type of reaction? Double replacement gas formation. So H2O plus CO2 plus and HCl. Now balance the equation. And that's easy. Everybody is good about that. I need 2 HCl, of course, here. And 2 over here. That takes care of it. So now I have 1 to 2. 1 Na2CO3 equals 2 HCl. That's what I have. All right. So let's go over here. And I'm going to say 1 mole SC, 2 mole SC. And the last part, that's very easy. And Ethan, can you tell us the last part, please? Mr. Shaw. Could you sing it for me if you don't want to talk?
It's 110, right? 110 grams of Na2CO3 over 1 mole.
110 grams, is that what you find out?
Yeah.
I beg to differ with you, slightly less than.
It's 106, right?
Yeah, 106 is right.
Okay.
So 106 grams, we'll just say 3 feet, 6 feet, that's okay, of
Okay.
SC divided by 1 mole SC. And that's done because we have the grams. So you can do the calculation yourself and then,
My calculator just died. Can anyone give me the answer for that?
oh please,
Huh?
tell your calculator not to die next time.
I don't know what's going on. I mean, I've had this calculator for like 7 years. So I think the battery, it dies so quick. I don't know why.
Well, you can
Everybody-
use your cell phone.
Everybody's having like technical issues today.
Dude, my calculator is just going downhill. It's a nice one too. I guess I could probably replace the rechargeable batteries. That wouldn't be a bad idea.
Somebody tell us the answer, please.
687.
687.
Yeah,
7.
yeah, 0.687. Because you want 3 6 figures, right?
Yeah, because we took 3 6 fig here, 106 grams. So yes,
All right, 0.687 grams. That's
687 grams. Okay. Now, calculate the mass of impure substance needed for the reaction. Remember this sodium carbonate is only 95%. The rest is something else. So what is that mass, impure mass? And is it going to be bigger than 0.687 or smaller than 0.687? How are you going to set it up?
It's bigger.
It's bigger, very good. That's one first thing to understand. Now, can you set it up with a dimensional analysis? You should be able to. How different?
I did too.
I'm gonna go get my charger.
All right, let me do my calculation here then.
I got 0.672. Well, it'll be 0.673 if you round up. What did you get?
Did you times the first two and then divide by 2 and then times by 106?
Yes, I did that.
Yeah, that's what I got to 0.64.
Oh, I know.
Well,
I'm
you guys
I'm
can
missing
find
it. I'm missing. I know what I did. I put 0.315 instead of 3015.
Okay, you guys are good at calculating. So
No, we're
you,
not. Okay, yeah, I got 0.643, which will be 0.644.
okay, we'll go with that. So we'll go with 644. 0.644 grams.
Yeah, that's what I got.
All right. Now, the next part. How are we going to do this? I want you to use dimensional analysis. It's a one-step dimensional analysis problem. How do we do it? Okay, folks, somebody's gonna tell me, let's see who is gonna be. Michael Natividad, can you do this step for us? One-step dimensional analysis. What is going to be the starting quantity and what is going to be the conversion factor?
Is the starting quantity the 0.644 grams?
Very good.
And then do you times that by the 95%, or like you divide by, like, are you times by 0.95 or something like that? I don't
That
know.
is correct. I
Okay.
want you to do the dimensional analysis. You are right. So how would you write down? I want all the units, remember?
Yeah.
So which units are going to be in the denominator? Grams of what? This is grams of SC, right?
Yeah.
So grams of SC are going to be in the denominator. Which one is grams of SC? 95 or 100?
100? No, not, yeah, 100, no?
Is it 100% SC or is it only 95% SC?
Oh, it's 95%.
So it's going to be 100 grams of impure
Impure,
top.
yeah.
and 95 grams of SC on the bottom. There you go. So I cancel out the units. Grams of SC and grams of SC canceled out. And the impure is what is left over. And you do the math. I'm not concerned about that. Now we are going to do C. Calculate the volume of carbon dioxide formed at 1 atmosphere pressure and 20 degrees Celsius. So we have this many grams of SC that we used. How many grams of carbon dioxide is formed? No. Volume meaning how many liters of carbon dioxide is formed. So that's the problem number 3. Jonathan, can you tell us how to start this problem? Are you there? Jonathan.
It's,
sorry,
isn't it
I just joined.
isn't it V equals nRT over P?
Excellent. And RT over P. Now, which one I have, which one we have, and which one we don't have? Do we have pressure? Yes. Do we have temperature? Yes. Do we have R? Yes. Do we have N?
Yes.
Where?
The moles.
Yes. Moles of carbon dioxide. Where do we have it?
Oh, I guess we don't have moles of carbon dioxide.
How are we going to find it?
Isn't it just 1 mole of carbon dioxide equals?
How do you know it's 1 mole of carbon dioxide that was formed?
Oh yeah, that's true. I don't know.
From the chemical equation, right?
This many moles, this many grams of sodium carbonate produces how many moles of carbon dioxide? That is our question. You understand that now?
Yes.
So now we're gonna, this is our starting quantity, and you're gonna go from grams to moles and stop. Grams to mole and stop. Grams of SC to moles of SC to moles of carbon dioxide, mole CO2, and stop there. Do not go to grams of CO2 because we don't want grams of CO2. And then that mole is going to go into this equation. Very good. That's your N, not 1. That's your N. Okay, everybody's doing this, and if you don't know what to do, you're gonna ask me. And this should be done in 5 minutes, really. Now, I mean, you know, how much time should it take? Once you have the solution map, it's easy, nothing to it. You have the equation, you have the solution map, you have everything there. So but if you are confused, don't sit around there, just confuse on your own. Include me in your confusion, please.
Professor, is it 0.00601?
I don't know, I have not done that problem, but 0.0060, I want 3 sig fig at least, right? It looks about right, but I don't
Here,
know.
let me share my screen real quick,
Okay, that's a very good idea. Let me.
and I will finish this. Give me 1 second.
You can show you. Okay, that is.
All right, so 0.06008. Okay.
Mole of carbon dioxide.
Is that right?
All right, 106 grams, 1 mole of carbon dioxide. Yep, that's what it should be. Now, if you don't understand something, anybody, you need to ask the question. Because if similar question is in the exam, I want you to be able to do it right away and not take too much time to do that. So if you understand it, you will be able to do it. If you don't, I don't know.
Might be earlier. I didn't see it. Are we given temperature?
Yes, 20 degrees Celsius.
Oh, perfect.
But we have to convert the 20 degrees Celsius into Kelvin, right?
Yes.
Yeah. Hey, Lisa, what did you end up getting for volume?
I'm still working on it. What would R be?
R would you'd use the constant ATM, so 0.0821. ATM times liter over mole times column.
Oh, I forget that. And pressure is just 1 joule, right?
ATM.
Now, anybody who has been using this 8.184 or something like that for R, I have not taught you that. And there is nothing in the guidebook that gives you that number. So where did you get that number? Only 2 number I gave you in the guidebook. 0.0821 atmosphere liter divided by mole Kelvin, and 62.4 torr liter divided by mole Kelvin. So any other number does not work for us.
I'm pretty sure that's what I said, unless you're talking about something else.
Yeah, there's somebody used 8.184, and we talk about it later with that person, but I thought I would just talk about it now, right now, because I don't want that number.
Yeah, I think the problem is you can, if you look up online to try to find it, there's different calculations, but as long as you know torr and R calculation for ATM.
The units are very important. Whenever you are looking at online, number of students did that, and they did not get it right because they look at line and they don't understand what's going on really. And I look at line at the online before I do the questions. I don't want you to just be able to look at the computer and write down the answer. What is the point in learning? What learning you're doing? You already know how to look at a computer. So I'm not going to give you an answer that's going to be that simple as that, just looking up at the computer. That's not you are here for. You are here for learning, not for what do we call it? Copying.
Josh, I got 0.01924.
What are the units, please?
Kelvin.
Kelvin.
Everything cancels.
Joules.
It's in liters.
It should just be liters. I got 24.1. I don't know how.
I got something completely different from you guys too.
Well, all I did was, I plugged in. Obviously, there's 1 mole, right? CO2.
1 mole. How many moles CO2 did you make? Not 1 mole. We talked about that before. Point.
Yeah, I got 0.006 for the moles.
Okay, that's why I got
0.00601 mole.
0.006 mole.
Oh, see, I got 0.00608 because it's 3 sig figs.
Yeah.
Changes everything. Okay, 0.146.
Got that? I got that.
Yeah, that's what I got.
Are the units?
Liters.
What did you guys have set up? 0.00608 times 0.0821 times 293 divided by 1?
Yep.
Yeah.
And what'd you get?
0.146 liters.
You guys fight it out among yourselves.
Wait, so when did we calculate the mole CO2? I must have missed a step. I might have been either making some food or going to the bathroom.
Okay, somebody answer that question, please.
It's based off of the moles of the Na2CO3. It had a I believe it was a 1 to 2.
It's 1 to 1. There you go, Josh.
Okay.
That's the first step.
What are
Yeah, it's just basically converting the grams of the substance to moles, and then moles of CO2, and then converting that, or actually not converting that, just staying with the moles of CO2.
very good. So you use the solution map, grams of sodium carbonate to moles of sodium carbonate to moles of carbon dioxide, and you stop right there. Very good. Well said.
Thanks, Lisa.
Okay, how is everybody doing? Let me talk with the individual persons here. Let's see. Okay, Cindy Garcia, how are you doing?
You would. I'm okay.
Do you have any questions?
No.
Okay, Anthony Daise Marambire, please tell me, how are you?
Oh, I'm doing good.
Okay, you understand so far everything?
Oh, yes.
Good. Sarah Karimi, please. Karimi Sarah, please tell me how you doing. Sarah Karimi is not there. Okay, Jonathan Chi, you.
Yeah, I joined late, so I'm going back to part A.
Well, you're going back to part A, then you need to help. You need help. So let me help you. Tell me what I can help you with.
Oh, I'm just working through it. I saw the equation, so
So working through it. So you're not confused right now. You know what you're doing.
yeah.
Okay, good. That's good enough. Okay, America Calderon, how are you doing?
I'm good.
Lantram,
Hanging in there.
hanging in there. I want you to do better than hanging in there.
I know if I have any question, I'll ask you. Right now, I'm kind of working on with the other people in the group.
Good enough, thank you. Okay, Joshua, I guess you are doing okay. Zach, Ligon or Ligon? How do you say it, Zachary?
It's pronounced Lagon.
Lagon, thank you.
I'm doing good.
Okay. Michael?
Professor, can we have the rest of the day off, please?
Rest of the day off? What day?
Today.
Rest of the day off after what time?
Right now.
Right now. Well, you can, I mean, I would not know if you are not there.
What do you mean? Oh, see, but the thing is, you call on people.
Well, I call on people. So what do I do if you are not there? I'm not going to penalize a person because you are not there talking with me right now.
Yeah, but don't you prefer us to be in class? If I feel a little better.
Not a question of me. Don't you prefer to be in the class yourself? Ask yourself that question, not me.
Yeah, I know, but like I know, but don't you want us to be in class?
He don't care, right? He gets
Makes
paid.
me happier if you are in the class, yes.
Because this class is so long. Like this is supposed to be a lab where we sit in the lab, and this is so long on the computer.
Post lab, this is part of lab.
I know, but what I mean, like before the COVID, we would have been inside an actual lab where we have on.
I know. We can.
I know.
all harp about that. I know. Yeah.
I
Yeah,
know,
yeah.
so heartbroken. But that's what I was asking. Maybe we should get the rest of the day off because we've been on here since the beginning of the class, and it's a
Yeah.
long class. We on here for like almost 5 hours.
You know, I really appreciate when students like to give me free money, but I don't like free money.
Free money? What's that?
If I'm not working, if I'm not with you, I'm not doing anything for the class, but I'm getting paid for it. That's free money.
But you giving us a peace of mind, so you giving us a break, so we can need to clear, relax, not have to think about work. I just feel like I'll feel so much better if I can leave and relax on your permission. Because if I leave on my own, I'm gonna feel guilty about it. Because I'm gonna feel guilty about it because, oh my God, I should have been in class and I should have paid attention. Like, need to be in class. But if it's on your permission, like under what you let us go, I feel a whole lot better and I can relax.
I understand what you are saying, and I appreciate you are being a very what's the word? You are communicating real well. So that's nice. And if I feel guilty, if I let you go early and I get free money, I feel guilty.
You shouldn't feel guilty. I'm pretty sure you're stressed out about us too. Because
You guys get paid really, really
That's
good.
easy for you to say. Why don't I say you shouldn't feel guilty either?
Yeah, but the thing is, you're the professor and you know it all. We don't really know it
Hey,
all.
hey. Have I ever said I know it all?
You know most of this thing because you teach it, and this is like obviously
I know something about how to teach this class, and I
you're
know
a professional at it, so
that
you
doesn't.
wouldn't feel too guilty. We would if we leave and we don't know what we're doing and we get a terrible grades, and now you're gonna have to hear us.
Well, if you get a terrible grade, you think I'm not gonna feel guilty?
I guess, but like in order for us to get good grades and enjoy life, we need a break, relax.
Oh, I can so surely understand that. And once we have gotten our work done, we can relax. So talking about relaxing is 3:35. Let's take a 15-minute break, okay? I can give you that much. 15-minute break right now.
That's good enough.
We'll be back at 3:50. Thank you. Thank you.
This meeting is being recorded.
Oh, I don't want to.
The recording has stopped.
All right, folks. So you have calculated the volume of carbon dioxide. And you understand that PV equals nRT. PV equals nRT is the equation to use, but we don't have number of moles. So we have to first calculate the number of moles of carbon dioxide made. And it is not 1 mole. It is what was made in that experiment. It cannot be 1 mole. It has to be different mole, most likely. So we first do that. Grams of sodium carbonate, 2 moles of sodium carbonate, 2 moles of carbon dioxide. There we go. Yes, we found the moles of carbon dioxide, and then we put that moles of carbon dioxide in the equation PV equals nRT. And please read the guidebook. I suspect some of you don't even have much of a read in the guidebook. I suspect that because you look it up in the wherever online. Well, why don't you look in the guidebook instead of looking online? Griping teacher doesn't sound very good. When teacher gripes, their voice goes kind of north instead of going south. But let me come back to south now. All right. So problem 2. By mistake, a student added some extra hydrochloric acid to the beaker containing dissolved baking soda. After the color change happened. So you understand the color change? Color change happened, and then the student went on going by mistake, which I have done too. She realized that she had added 40.30 milliliter 0.3015 molar acid to the 25 milliliter solution containing 1.245 gram pure sodium hydrogen carbonate. So this is our pure sodium hydrogen carbonate. Calculate the molarity of hydrochloric acid in the beaker. Calculate means show the stoichiometry setup and the answer. That's what calculate means. You have to show that. You cannot just give me the answer. If the answer is right, I might consider giving a little bit of a point. If it is wrong, you don't get any partial talk credit. But if answer is right, I might even suspect that you just ask your computer and somehow got the answer without really knowing how to do it, which is not learning. So I don't want to go into that suspicion business. So, calculate the molarity of the hydrochloric acid. So we are going to first say what is molarity. Molarity is moles over liter. Do we know the moles and do we know the liters? Well, how many moles of liquid is in there? Or how many liters of liquid? I'm sorry. You can do that. So everybody tell me how many liters of liquid is in that beaker. Do that problem, that part of the problem, and get me the answer.
Would it be 40.30 ml?
Was there also some other liquid there?
Yeah,
Okay, so
I got 0.0653 liters.
So you added up those two liquids, 25 plus 40.3,
And then divided by 1,000.
right?
Yep.
So that's many liters of liquid we have. Now, do we know the molarity? Do we know how many moles of acid there is there? No, we don't. So we need to calculate it. How do we calculate moles of acid? This is our question.
well,
Moles yes, go ahead.
it said she realized she added 0.0. She added 43 ml moles of acid. She realized
Yeah.
she added.
Right. So we know how much acid was added. Do we know how much it was used up? The acid reacted. So not all of that acid is still in there. Only a little bit more is there because you added extra. So how much extra acid is in there? How many moles of extra acid is in there? That's our question. Very good. We are getting somewhere. How much acid we put in and how much acid got used up. So the extra acid is going to be how much acid, meaning how many moles of acid we put in, how many moles of acid got used up. And difference of the two would be the extra acid, extra moles of acid. So that's what we need to do. Do we know how much acid we put in? Or how much acid was used up from the last problem? Can we find that out? We have 1.245 grams of pure sodium hydrogen carbonate. How much acid would it use? How many moles? So I want you to do that calculation. 1.245 grams of sodium hydrogen carbonate. Now we are talking about sodium hydrogen carbonate again. We are not talking about sodium carbonate. And how much acid, how many moles of acid would be needed to react with that? So what is going to be your solution map?
Is it grams SHC to moles SHC to moles acid?
Very good. That's it. Stop right there. Very good.
And then you use the molarity to find.
Let's write that down. We don't need to do the molarity yet. We just need moles. We don't need milliliter of acid used. We just need mole of acid used. Because we want to use the mole of acid that is still in there to find the molarity of the acid for the whole solution, which is 65 milliliter. So all we need to do is to go to moles, grams to moles to moles. So everybody knows how to do that. Grams of 1.245 grams sodium hydrogen carbonate to moles of sodium hydrogen carbonate and to moles of acid. You have the equation, balanced equation. You know the molar mass of sodium hydrogen carbonate. You know the solution map. Go for it.
What was the moles of sodium hydrogen carbonate again? I'll find it.
Oh, that was 84.01 grams per 1 mole.
4.01. 84. the acid added was HCl, right?
That's correct.
Okay, so it's the one mole SHC to 2 moles HCl.
No, just 1 mole HCl, or yeah, 1 mole HCl.
I'm just looking at the
Balanced equation.
post lab. I have 2 HCl online.
No, just 1 mole. Yes, we are talking about sodium hydrogen carbon, not sodium carbon.
Okay.
That's why it's 1 mole to 1 mole. Okay, who is needing help? Makaya, are you needing help?
No.
All right, thank you. Jonathan, are you needing help?
I don't think so, but can I check with you?
Sure.
So we took the grams of sodium hydrogen carbonate, and then we multiplied that by moles per grams for sodium hydrogen carbonate, and
Good.
and the moles for that to hydrochloric acid is 1 to 1, right? So
Right.
that
Yes.
it would be the same moles.
Right.
And then you told us to stop there,
Yes.
right? Okay.
Right. All right. Yay.
For molarity, I got 0.2269. Did anyone else get that?
I got that too.
Sweet.
0.2269? No.
0.2269 mole per liter.
No, it's too high.
I got that from moles.
Oh, I thought the moles were 0.01482 because
That would be the total, but when you subtract it, that would be the extra.
Yes, good. Tell us about that. Subtraction.
Wait, so where was the subtraction? Sorry.
You had let's see, you did 0.0148 minus the moles for hydrochloric acid, right? Which is 0.01215.
No, that's not what I did.
1.245 grams of SHC equals how many moles of HCl?
I got 0.01482, but I don't think that's correct.
No, that's for that's moles of sodium hydrogen carbonate, which is 1:1 with hydrochloric acid.
Yeah.
So therefore,
Great.
that many more 0.0142 moles, is that correct?
That's what I got.
Okay.
If it's a 1-to-1.
Yeah, it's a 1-to-1. Now this much HCl got used up.
Okay.
How much HCl, how many moles of HCl did we put in there?
I got we put in less. Am I putting something wrong?
Let's find out, let's calculate it. There must be more because there was extra HCl put in there. So we would do this. What is the solution map? We want moles of HCl that was put in there. So what do we start with?
Oh, actually, I think he's right. There were less, because if you multiply the 0.0403 liters by
Right.
the molarity, you get point
Liter
um
by the molarity.
yeah,
Molarity.
you get 0.012, but then it says the amount used up was
301310 mole, right?
yeah.
Okay, so that gives us the moles of acid that was actually put in there. So what's that? What's that mole?
It's 0.01215.
0.1215. Oh, yeah. Mole HCl.
There's a 0 in front of the 1.
Oh yeah, right.
So it's less.
A. It is less.
But it changed color, so it had to have been more.
Ah, I thought I did the right calculation and it should have been more. Dang, dang, dang. All right, how am I gonna deal with this?
Oh, I think I got what you're saying. And then you just subtracted the. So we just calculated the moles of the acid, and we got the moles of the acid actually used in the solution. So you just subtract those two, and that should be.
The moles of acid in the solution.
Yeah.
And then you divide that by the 65 milliliter.
Yep.
Yeah, but what we are seeing here is that what was pointed out just now is that the used up moles is bigger than the mole that we put in there, which cannot be. So then that means there was not enough HCl in there actually. So if that is the case, if there is no calculation mistake, it's my mistake. Not, that would be my mistake if that is the calculation mistake here. 1.245 grams divided by, let's see, I'll do the calculation again. Yeah, that's what it is. Okay, tell you what, guys, I'm gonna do this. I'm gonna make this 1.000 gram pure sodium hydrogen carbonate instead of 1.245. And you guys are responsible for doing the calculation. So everybody change your number to 1.000 gram pure sodium hydrogen carbonate instead of 1.245. And then you do the calculation, and we just explain to you what to do. So you do it now.
It is less.
I have been made feeling guilty by somebody in this class by telling me that I'm not letting student have a little rest. I'm feeling guilty. So I need to do something about that.
It's just so, it's a lot of time to be looking at screens. I feel like when you're in lab, at least my experience, and
Yes.
you do get some downtime. Like you are working
Yeah.
pretty much, but there is downtime, and you're not staring at a screen.
I agree. I agree that you're right. Yes. And you know, the person, I appreciated that person being so communicative about it. So I need to do something about it. Otherwise, what's the point of appreciation, right?
Mhm.
Yeah, yeah. So I gave you a little break, and that person was very nice in saying that helps. So now what do we do now? I'm gonna leave this to you guys to do. I have explained how to do it, and you guys do it later. And then we're gonna do a little more, and I'm gonna let you go early today.
Yay.
So what more we gonna do? And if somebody wants to hang around and ask me questions, that's okay with me. But you guys, you don't need to feel guilty about leaving me without letting me know. All right. So let's go to the next part, little bit that we want to do today. Little bit of the next part, and that little bit of the next part is right here. We need to finish the unit 21. That's what I want to do. Just 2 more problems, examples, and then we'll be done with it. Example 4 and example 5. We did this example 3, 4 and 5 I'm gonna do, and then we're gonna be done. And I'm not gonna bother you too much. I'm not gonna ask you questions. I don't wanna put you on the spot right now because you guys are feeling, or some of you are feeling really feeling the tired because of looking at the screen. Yeah, I understand that. Okay, answer is given here. Calculate the heat released when 200 milliliter 1 molar hydrochloric acid reacts with 200 milliliter 1 molar NaOH. This is a neutralization reaction. It is a reaction that is an exothermic reaction. Energy will be released. Energy will be released. And when energy comes out of the system, that is a negative sign to that energy. So negative Q is what we are talking about. And we have a reaction going on. So first we need to do is to write the equation for the reaction. So that's very simple equation, HCl. AQ, please always write AQ for acid plus NaOH. With NaOH, this is solution, of course, 1 molar. So it is also AQ, but if you don't write it, I'm not gonna be too unhappy about that. But HCl AQ, you don't write that AQ, I'm unhappy. All right, NaCl plus H2O. And here you don't need to write anything else. You don't need to write NaCl aqueous or H2O, whatever, liquid. So that's the equation, a reaction is happening. And Q is the next thing. So we're gonna say Q, negative Q, of course, because it's an exothermic reaction. The system, this is the system. This equation represents the system for us, a chemical system. And the system gave heat away. Things got hotter. This is an exothermic system. Therefore, it released energy into the surrounding in form of heat. So the Q is going away from the system, and therefore we call it negative Q. So when you are thinking about the sign of this Q, you are always going to ask the question, is the money came in my pocket, or did the money go out of my pocket? If the money went out of your pocket, you are the system. If the money goes out of your system, your pocket, then it's negative sign. If the heat goes out of your pocket, your system, that's a negative sign. If the work goes out of your pocket, you get tired. You do work, you get tired, energy went out of the system, that's negative for you, right? That's how you look at it. You look at it from the point of view of the system. So negative Q equals grams multiplied by small c, that is the heat capacity, and multiplied by delta T. So we write it down. Grams are given to us. Assume 400 grams. All right, then we have heat capacity is 4.18 joules per gram degree Celsius. Please, please, please always write your units. Multiplied with 19 to 24.1. So that's 5.1 K. Now cancel out your unit, be nice and cancel out your units. And so you can tell you have done it right or not. Gram and gram cancel out. Degree Celsius and Kelvin cancel out. We are left over with joules as the unit, so that is correct. So we have it done it right. And we do 40 multiplied by 184, 400 multiplied by 4.184 multiplied by 5.1 equals 8. I want 3 significant figures. Oh, I want only 2 significant figures. Whoa, whoa. 8.5 multiplied by 10, oh no, 10 raised to 8.5 kilojoules. I'm gonna make it, instead of joules, I make kilojoules. So I don't have to write that whatever, kilojoules, kJ. There we go, 8.5 kilojoules.
Don't you have to, if it's kilojoules, don't you have to take it by 1,000 backwards?
Yeah, so that's what we are doing. I got 85,353. Oh,
Okay.
no, yeah, 8,535
Okay.
joules. And so
And,
I made it into kilojoules by doing this.
is it negative or can
It is
joules not?
negative. Thank you for reminding us.
And generally, do you want it in joules or kilojoules? Do you prefer it?
Kilojoules is easier for us because joule is such a small unit of energy
Mhm.
that it's always going to be a lot. Like, you know,
I got
a banana has 160 kilojoules of energy in it.
All right.
Okay. And later we are going to calculate what happens if somebody does 10 push-ups, how many joules of energy this person is using.
Mm.
Yes, that can be calculated. All right. Now, that's all.
Beautiful.
So we did not use any of this. 1 molar hydrochloric acid and 1 molar NaOH and 200 milliliter and 200 milliliter. We did not use any of this. Assume 400 grams, that goes right into the equation, and there's we got that. And so this is important to know what we did, but it is not part of the calculation. So I should have only 2 sig fig over here. 8.53 instead of 8.53, it should be 8.5. All right, next one. That's the last one. And don't tell me ever that I did not let you go early. But if you want to hang around with me, I'll be happy to do that. That way I'll feel less guilty. Remember that? An exothermic reaction rises the temperature of a coffee cup calorimeter, heat capacity, this, and the reaction mixture Okay, from 18 to 28 degrees Celsius. Isn't the same question that we did earlier?
Yeah, I think we did both of these.
Yeah, we
Yeah.
did both of those.
Yeah, well, then we are done with
Hey, I like going over problems again. We can finish up 5 one more time just to make sure I got it.
In that case, you are going to do it and we're gonna listen to you.
Uh-oh. All right.
So
So-
here you go. I'm gonna give you the control.
Give me the it's I'm doing it on my lab book, so it's
All right, whatever you want.
try to just vocalize my rationale for it.
Okay, good enough. Go ahead.
Okay, so we're talking about example 5, right?
Yes.
Exothermic action raise the temperature of a coffee cup. So we have Q reaction equals
Very. That's the first equation, simple equation. Q reaction equals.
30 grams of liquid.
yeah, 30 grams.
No, we are just gonna write down where did the heat come from and where did it go. That's the first equation. We're not gonna have anything but Q in that equation.
Okay, is it so Q reaction equals Q liquid plus Q metal?
Calorimeter. That's where it went.
Calorie meter?
Right, calorimeter, some heat went into the calorimeter and some heat stayed in the liquid. So we have two.
Okay.
Negative Q reaction equals Q liquid plus Q calorimeter.
Okay. And so going from that, you have Q, we have our 30 grams liquid. So Q 30.00 grams times, do we know it's, so we're just using the specific heat capacity of water, 4.18 joules over grams times Kelvin.
What is given to you, specific capacity of the liquid is same as water because it's almost water anyway.
Okay, yeah, it is given to you. Okay. And then you multiply those two together, and you're also going to be multiplying that with Kelvin. So you cancel out your grams, cancel out your Kelvin.
Right.
The change in temperatures from 18 to 28, so that's 10.
So that's 283.
Hmm?
Is that 283 Kelvin?
I think it's, I guess you could go Kelvin, but can't.
Yeah, we can't do that.
Should we-
10 Kelvin.
Keep it in Celsius?
No,
I think they're interchangeable, right?
it is the same thing. Kelvin and Celsius is the same when we talk about delta T.
Okay.
Okay.
You want me to show it to you again? Why?
No,
No.
I think we got
Okay.
it. All right, so multiply that by,
Is that you have to add both of the times. You have to add 273 to 18 degrees and 272 to 28 degrees.
and it would still be 10. Okay,
So
perfect.
then it cancels out and it's only with 10.
Okay, so multiply that by 10 Celsius, or you can write Kelvin, doesn't matter. And then that, I got 1,245, and that would be in joules, right?
Okay, so that's 1.5 kilojoules.
1 point.
Well, that's okay. That doesn't matter. Yeah, that's fine.
Okay, and then I guess we'll just change that to kilojoules. So 1.25 kilojoules. And then, what is this? Okay, I'm trying to see how we get this negative 0.215. Is that from the heat capacity of the cup?
Right, for the calorimeter. That's right.
Okay.
And heat capacity, what are the units of heat capacity? They are given to you. Look at that.
Joules over Kelvin.
Yeah, so you only have to multiply it by Kelvin in order to get the Q.
Okay. And then our Kelvin in this case.
I mean, the same as the liquid, because liquid and the calorimeter are in contact with each other. So it's going to be 10 degrees, 10 Q, 10 Kelvin.
Oh, that makes sense. Okay. So then you take 21.5 joules over Kelvin times 10 Kelvin equals 215, and that's joules, and then you're going to convert that to kilojoules, right? So you just move the decimal place three over. So oh yeah, 0.215 kilojoules, and then you subtract 0.215 kilojoules from, or you subtract 1.25 kilojoules from that number, and that should give you a reaction.
The total. So no subtracting, adding both.
Oh yeah, because it's negative.
Because Q total equals, you went into two places from the reaction. Okay, that's it. That's it. If you want to hang out with me, it's up to you. If not, well, feel free to go and don't feel guilty. All right?
Hey, Professor,
Go ahead.
can we go over the lab problem too? I don't know how to set this up. And I can share my screen and show you what I have so far.
Yeah, fine.
Okay.
Okay, I'm gonna get out and you have your scene. Share the screen. Stop share. Okay, here we go. Go ahead.
So this is what, can you see?
Yeah, I can
doing
upside down or side up sometimes.
Is that upside down?
There, no, the other way. There, stop.
That way.
Yeah, there. Okay.
Okay. What am I doing wrong?
Let's
One
see.
mole. What grams do I put in here for the NaCO2?
1 gram, yeah, I told you to do it.
This one, the
Yeah,
1.243?
I asked you to get rid of that and put down 1 gram.
1 gram.
Yeah.
Maybe that's where I got lost. Okay, so 1 gram.
Okay.
And then so gram over mole. So I just add what this
Molar mass is
106.
No, you want to take Na2CO3? I gave you NaHCO3. Okay. All right.
Yeah, so 106.
Yes.
Oh, I thought it was 84.01. That's what I have on mine. Okay. It's
That
106.
was NaHCO3. That's where we are getting mixed up.
So SHC is 106.
SHC is 84. SC is 106. I don't mind either way you do the calculation, doesn't make a difference to me. It'll be a little different answer, but that's okay.
So Na2CO3, that's 106, right?
That's right.
Okay. And then it's just for 1 mole, and then they're mole to mole.
Oh, well, there is going to be 2 mole now. 2 moles
The
of
HCl
equals 1 mole of HCl. 2 mole of HCl, right? You're right.
Okay.
Okay, now we stop. We find the moles.
Okay. Awesome.
Wait, I thought we were saying it was 1-to-1 that whole time. It's 2-to-1, right?
Because she has Na2CO3, that's why.
Okay.
If it is NaHCO3, then it would be 1-to-1.
Well, do I have it wrong?
No, I mean, we could take it that way. I mean, well, what do you want to do? NaHCO3? Start with NaHCO3 then, because the problem says NaHCO3, leave it NaHCO3.
I'm really confused now.
Well, the problem says NaHCO3, right? That last problem.
Yes.
So that's why we want to just keep NaHCO3 instead of Na2CO3 here. 1 gram of
Um,
1 gram of NaHCO3 right there,
and then it's 84.
and then it's 84.
Yeah. And then is it 1 to 1 too, and not 2 to 1?
NaHCO3, change the formula here. NaHCO3 here. Every place, NaHCO3.
And we're just writing that as SHC, right?
Yeah, you can write it at SHC.
And it's 1 to 1, right?
Yes, then it's 1 to 1. Okay, what is the next step? We have moles of acid that's going to be used up. This is the mole of acid used up. Write it down.
This is the mole of acid that's going to be used up.
Right, because that's going to react with NaCO3. That's gone.
So that's 0.2269.
Really?
I got 0.01190.
Right. That's.
And then we know that too because
Multiplied by
it needs to be lower.
4.
Yeah, I got the same thing, 0.011.
0.
Okay, so that gives us our mole HCl used up, right, Professor?
Now we're going to calculate how many moles of HCl we added.
So we added, it says, so that is that where we use this 40.30 milliliter?
Right, that's what we added. Yes.
Okay, so wouldn't it just be, you would just, let's just say we start with.
First 2 moles, that's all.
Okay, that's easy enough. So you just, I'm going to start at liters, so I'm going to move it over 3. So 0.0430 or 0.0403.
Is it 0.40 or 0.4030 or 0.0?
0.0403. Because
Okay.
you move it over 3 times. Divided by 1,000. Okay, and then that's your liters. And I'll just say liters HCl. And then you're going to multiply that by molarity, which is
0.3010.
0.301. It's 0.301, right?
0.3015 though, out of the problem?
Yeah. And then divide that by 1 liter. Then you're going from liters to moles.
And then we just stop, right?
It's still too much.
Like this,
Oh, no.
right?
Okay, you guys, what I'm going to do, I'm going to refurbish that question and change it in that in the canvas, and you will see some different numbers. Okay, that's all. Now you know what you're doing.
Why would you do that?
Because because it needs to be clear. It needs to be clean, and this is a mess that I made myself.
Yeah, but if you change those numbers, okay.
It's a simple thing. You just do the same calculation, but
Why don't you change it right now and then we'll just hold off and do it together.
Ideally, too, Professor, I work 12 hours shifts the next 3 days.
I know.
So it's gonna be hard for me to get this in. Ideally, I'd get this and the homework done tonight. So I'm just
Yeah, that's what I'm trying to do too.
Yeah, same.
So why don't we just finish with this problem? So you would just take the 0.04030 HCl,
Mhm.
times that by 1 liter HCl, times it by the mole, and
Yeah.
then you get 0.01251 moles of HCl.
Yeah.
Probably have to redo the calculation because I had 0.3010.
Okay. And so
So-
subtract one, subtract from that, and then you have the answer. All right, fine. That's enough.
Okay, so when you say subtract from that, we're subtracting the mole of HCl used up by this, and so it's gonna end up being, it's gonna be 0.0121, or I guess we'll do 4 sig figs, 1215
Okay.
minus this
Yes.
number that we got before, 0.0.
Right. Very, very little is left in there.
Okay, and then that's gonna leave us with, I'll just do it right now.
Then you are going to divide that with the 65 milliliter or 0.065 liter.
Yeah, I got an insanely small amount, but there's still some.
Yes, extremely small amount. Yes, true. The molarity is very, very little. Right.
Okay, so I got 2.505 4 sig figs times 10 to the negative 4.
Okay. Good enough.
And then that, at least, do you want me to share my screen? It might be a little easier to read.
Oh,
Yes,
I
please.
understand what you're doing. You're fine. Go ahead. Share your screen if you want to.
Okay. So I think the only thing I'm having a little bit of confusion with is just having like a firm understanding of what we're actually doing. Because I understand that we calculated what's used up.
Yes.
And then we're also finding the moles added.
Right.
And then we subtract those because not all of it that we added was used, right? And that's why we get this.
Moles of HCl we are left over with. We found that.
Okay, and then this is,
Molarity is mole divided by liter.
yep.
So moles is of HCl in that solution, and you know how many liter there is. There is the molarity of the HCl in the solution.
And so we just take this number, molarity equals HCl equals, we have our moles, and we're subtracting that by the full amount, the total
That's right.
total liters, right? So then we're just gonna have this number. Okay. One, two, three. Does that look right? Professor, does that look right?
Yes, looks fine.
And so pretty much what's left in this lab, we just have to fill out, we just have to do the 2 more calculations for here.
And then just use the equations to plug and play.
Cool, easy peasy. Is this technically a row or a column?
Row. Like remember the Greek row, columns. in the Parthenon and other places in Greece.
Mhm.
Those are the columns.
Oh, you know what? I like that. That's not bad. Okay, Professor, you said you're gonna find this, you're gonna calculate the percent error, so we're gonna leave this alone.
That's right.
Okay. All right. I mean, it seems pretty doable. I will say, Professor, I think that I think there was enough time on that quiz. At least I felt comfortable with it.
Well, I'll tell you about that in private.
Okay.
Well, I'll tell you anyway. Well, no. I won't do that.
Sure.
It's a personal conversation.
You got my number.
I don't know. I don't have your number. You send me text message, but I don't know who it is unless you write your name on it. All right, folks. It's 4:40,
We did it.
and I'll see you in 50 minutes at 5:30.
All right, sounds good.
Whatever is coming, whoever is coming, we'll see you then.